This is G485 homework booklet, question number 27. Describe the formation of a star such as our Sun and its most probable evolution. Looking at the end of this question, we can see that 6 marks have been allocated. So to think how they would be awarded in practice, the mark scheme requested 5 of the following 6 points that we have listed here, but the 6th mark was the quality of written communication mark, and that was awarded for correct sequencing. So looking at these lists, you need 5 of the following 6, but within each of these numbered statements there are sometimes alternatives shown by the diagonal line. So be careful, you couldn't be awarded both of those points. So looking for 5 points then, and in a logical order. First of all, a cloud of gas and dust is drawn together by the force of gravity. Secondly, the mark is for describing the energy changes in this situation. So as the material is drawn together, potential energy changes to kinetic energy. You could alternatively point out that this leads to a rise in temperature. The third point is about fusion taking place. So we have fusion of protons, or you may say hydrogen nuclei, which releases energy. Make sure that if you talk about hydrogen and helium that you use the word nuclei. That's important. The 4th mark describes the stable state of the star. So this happens when the radiation pressure is equal to the gravitational pressure. You could say that outward forces due to the radiation pressure equal the inward pull of gravity. The 5th marking point is again a later stage because we're going in order. So ultimately hydrogen runs out, and this leads to the outer layers of the star expanding. An alternative marking point is describing what happens to the core. It shrinks. And finally, you get a mark for either saying that a red giant is formed, or for referring to the fact that eventually the core becomes a white dwarf. Next part of the question, we just have 2 marks describing the probable evolution of a star that is more massive than our Sun. So more massive stars end their evolution more dramatically with a supernova. And following the supernova, we would expect either a neutron star or a black hole to be left behind. Part B. So now we have a calculation to consider. The present mass of the Sun is 2 × 10⁻30 kilograms. The Sun emits radiation at an average rate of 3.8 × 10⁻26 joules per second. You should identify these units as the units for power. Calculate the time in years for the mass of the Sun to decrease by 1/1,000,000th of its present mass. So you need to consider how 1/1,000,000th of the mass of the Sun will be converted to energy. 1/1,000,000th of a mass of the Sun takes the value here, 2 × 10⁻30, and multiplies by 10⁻⁻6. And the energy conversion corresponding to that mass is given by the equation delta E equals delta m c squared. So here we are multiplying by c squared. giving the corresponding energy in joules. Now, looking back at the question, you were asked for the time in years for the mass of the Sun to decrease by this amount. Identifying this as power and thinking that power is energy converted divided by time taken, rearranging that, we have time is energy converted divided by power. Now be careful, the units here are joules per second. We have a change in energy in joules, so our answer for time using this calculation is in seconds. So the last step is to convert that into years to match the question, and on the data sheet you will find the number 3.2 times 10 to the power 7 as the number of seconds within a year. So that leads us to the final answer here of 1.5 times 10 to the 7 years. The next part of the question asks you to consider fusion in more detail. So we are given a nuclear equation summarising fusion occurring in the Sun. You are asked to explain the process of nuclear fusion in the core of the Sun. Note the question asks you to refer to conditions necessary for fusion to occur. You must always respond to points like this given in a question. 4 marks are allocated, so you need any 4 points from the following 6. So first of all, what is fusion? It is protons or hydrogen nuclei fusing to form helium nuclei. Remember to use the word nuclei whenever talking about fusion. Avoid atoms. Secondly, thinking about conditions necessary and how fusion would be achieved, there is the problem that electrostatic repulsion exists between protons. So there would need to be a force to overcome this. The condition to achieve that is high temperatures of the order of 10 to the 7 Kelvin. And at these high temperatures, the protons will be moving fast enough to enable them to get close enough so that the strong nuclear force can come into play and overcome the electrostatic repulsion. Remember that the strong nuclear force is a very short-range force. The next point explains what is achieved during fusion. The decrease in mass corresponds to an energy released. You could express this alternatively by referring to the increase in binding energy. Finally, you could comment on, again, a condition for fusion. It occurs where there is high density or high pressure in the core of the Sun. Next, 2 forms of energy produced in thermonuclear reactions. First of all, we have kinetic energy. The mark scheme did not allow heat or thermal. So think about the products of this fusion reaction and you can consider them to have kinetic energy that they gain as a consequence of the mass loss. The other kind of energy formed is electromagnetic, or you may refer to photons. Please do not say just radiation. The mark scheme did not award that a point. And finally, a calculation. You are told the binding energy per nucleon of hydrogen and helium. They are respectively 0 and 7.2 mega electron volts. If you think about it, a proton is one particle, so there is no energy binding the protons together. Following then, we are asked to calculate the energy produced in joules for the fusion reaction given in the equation above. So we want to know, first of all, the change in binding energy. Now there is no binding energy associated with the protons. But when we have the helium nucleus formed, we have a binding energy of 7.2 mega electron volts per nucleon. There are 2 protons and 2 neutrons in a helium nucleus, so that's 4 nucleons, so the total binding energy will be 28.8 mega electron volts. Finally, note you are asked for the energy in joules, so you need to convert this. Now 1 electron volt is equivalent to 1.6 times 10 to the minus 19 joules. You should remember from 482 the equation for electrical work done, W equals QV. So an electron volt is the energy or the work done when an electron is moved through a potential difference of 1 volt. So you multiply the charge of the electron by 1, and this is why this is the factor you require here to convert to joules. So your final answer is 4.6 times 10 to the minus 12 joules.